Imagine you're 43 years old, you've got 3 kids, and you're running a household. You've got a job, you're doing everything. And over the last year, something has gone wrong with your brain. Maybe you can't focus quite the same. You've got lots of brain fog. You're feeling more fatigued. You sit down to do your work. Maybe you struggle to find the words, or your concentration is just not quite there. And by mid-afternoon, you're just so exhausted that you could lie down on the floor. So you do the responsible thing. You go to the doctor. Maybe you get sent to a neurologist. You have an MRI. The scan shows maybe a few small bright spots, what radiologists call white matter hyperintensities. And you're told it's just normal. People your age have these. There's nothing to do. Come back if it gets worse. So you go home and you wait for it to get worse. Meanwhile, you're still suffering with the brain fog and the fatigue, and nothing's really changing. Maybe that concentration is gone. You can't focus the same. You're not as productive as you should be. And that's a real pattern, not that exact person, but that exact story playing out in clinic constantly. I see this all the time. And today I want to talk to you about something that almost nobody tests for, that may sit underneath a lot of these stories. And it's a barrier that is inside your head. When it's working, it's one of the most elegant pieces of engineering in your body. But when it fails, it's quietly changing everything. This is the blood-brain barrier. Welcome back to the Good Health Podcast. I'm Nicole Good, certified functional medicine practitioner, and your host for today. And today is a deep one, but hopefully it's also a hopeful one. I do want to set up expectations. Some of the things we're going to be talking about today are really solid textbook neuroscience. Others are promising research. So there is always more research to be done in this area, and I will flag where this changes. But what I really want to discuss with you today is why the brain is different from the rest of you, the importance of this blood-brain barrier, and what we can do about it. So with that, let's jump straight into today's episode. Here's a fact that doesn't get enough attention. Most of your body is constantly rebuilding itself. Your skin cells turn over. Your liver is famous for it. You can lose a chunk of liver and it's going to regrow. Your gut lining replaces itself every few days. Your immune system is pumping out fresh white blood cells from your bone marrow around the clock. Cut yourself, get sick, take a hit, and there's a resupply line. Your brain mostly doesn't work that way. The main working cells of your brain, your neurons, are what's called postmitotic. So for the most part, once you have them, they don't divide to make new ones. You're largely working with the set that you've got. Now, there is nuance here. Researchers have found that a few specific regions, like parts of the hippocampus involved in memory, can generate some new neurons in adulthood. And we do regenerate, we do get new pathways. And that's a real and active area of study. But it is limited, and it doesn't change the big picture that across most of your brain, neurons are not mass replaced. Heart muscle cells are similar, which is in large part why something like a heart attack does such lasting damage. So the brain has a kind of vulnerability that the rest of your body maybe doesn't. You can slowly lose ground over the years, and there isn't a generous resupply waiting in the wings. This is the quiet question sitting behind aging. How much of this brain do you get to keep? Now, the brain also has its own dedicated immune cells, the most important being microglia and astrocytes. Collectively, they're called the glial cells. And here's where it gets interesting, because these immune cells behave differently from the immune cells in the rest of your body too. So out in your bloodstream, immune cells are dynamic. They ramp up, they calm down, they die off, they get replaced. You've got regulatory cells whose entire job is to put the brakes on the immune response once the threat is gone. In the brain, the dial seems to be much stickier. There's a concept researchers call microglial priming. And this is the idea that once these brain immune cells get switched into an activated and inflammatory state by a serious enough insult, they don't always switch back off, or not all the way back off. So they stay on a hair trigger, they're primed. And the concern, based on the growing body of research, is that this priming can be long-lasting and hard to reverse. So permanent is a really strong word, and science is, of course, always changing and always maturing. But the working model tells us that the brain doesn't forgive insults in the way that the rest of the body does. It remembers them at a cellular level. And that has a real consequence for how you think about brain symptoms. If you sprain your ankle, you rest it, it heals, you forget about it. The brain may not offer that same clean reset, which is why the smart move is to take brain inflammation seriously and do it early rather than treating it as something that, you'll get around to one day. So how would you even know if your brain's immune system is in this primed state? You can't feel your microglia, but there's a behavioral signature that clinicians who work in this space, what we're looking for. And it's something that you can actually recognize in yourself or in someone you love. It's this kind of falling apart from trivial things. So a single glass of wine may wreck you for 2 days. A crowded or loud restaurant leaves you feeling foggy and drained in a way that seems wildly out of proportion. Maybe a minor bump on the head, nothing, the kind of thing that is forgotten about in an hour, sets off days of symptoms. One meal with a food that you're just a little bit sensitive to and suddenly you can't think straight. So the key word here is disproportionate. Everybody feels a bit bad after a night out or too much wine. That's completely normal. What we're talking about here is a reaction that is so far out of proportion to the trigger that it doesn't quite add up. So just a couple of glasses of wine and you're completely floored. This is the brain immune cells being primed and sitting on edge. So that small nudge that a calm brain would just shrug off as if it's enough, that will tip a primed brain over into a full inflammatory flare. The system has got no slack left in it. If this pattern sounds familiar, file it away. It doesn't diagnose anything by itself, but it's the kind of clue that we're always looking for, and it's the kind of clue that is really worth taking seriously and that you don't want to dismiss. So let's talk about the star of the show here. You've probably heard of leaky gut. It's everywhere right now. So if you're interested in health at all, you've probably heard of leaky gut. So the basic idea here is that the lining of your intestine is supposed to be selectively sealed, letting nutrients through and keeping the wrong stuff out. The cells are stitched together by structures called tight junctions. And when those junctions loosen, things that should stay in the gut start leaking into the bloodstream. And that can drive inflammation around the body. And that's a real and well-studied concept. But here's what far fewer people know. Your brain has the exact same kind of barrier, built from the same tight junctions, and it's called the blood-brain barrier. So picture the blood vessels that are running through your brain. Normally they're a little bit leaky. That's how tissues get fed. But the vessels in your brain are special. Their walls are sealed up tight. They're wrapped and supported by those astrocyte cells we mentioned, forming a highly selective gate. So tiny essential molecules, things like oxygen and glucose, they get waved through. Almost everything else is turned away. And this barrier is the reason that your brain can run its incredibly delicate electrical operations in a stable and protected environment, walled off from all the chaos of your general circulation in the body. And here's the thing that should make you sit up. The same kind of stressors that loosen that gut lining can loosen the blood-brain barrier as well. So the brain can get leaky in the same way that the gut can. But here's the gap. Walk into almost any clinic and there's a real interest in gut permeability. But almost nobody is asking whether the blood-brain barrier itself might be compromised, even in people whose symptoms are obviously coming from the brain. So brain fog, cognitive decline, mood symptoms. The default assumption is often fix the gut, the brain will follow. And sometimes it does. The gut and brain are genuinely connected, and we'll get to that. But sometimes you do have to look directly at the brain. The body isn't a stack of separate systems, it's a web. If the relevant strand of that web is the barrier around your brain, then no amount of gut work is going to fully address it. And this is why sometimes people come in and say, I've tried everything, I've done every diet, I just don't feel any better. So hold on to that question. Is the barrier itself intact? Because it changes everything about how you'd think about a case like the single mother that we mentioned at the top. So let's build a mental model. Broadly, there's 3 different routes by which the brain can become inflamed. And they're not equally dangerous. This distinction is the single most useful thing in this whole episode. So let's lay this out clearly. Road 1, we have direct injury to your neurons. So this is the obvious one. Physical trauma to the brain or a stroke. And in some cases, certain infections that reach the brain tissue. So some viruses, some infections can cross the blood-brain barrier. When neurons are physically damaged, so an accident, a stroke, or one of these infections that can cross that barrier, their long fibers, so the axons, can tear and they spill out distress signals. So proteins and inflammatory messengers that essentially are shouting, something's wrong over here. And those signals switch on the brain's immune cells. And critically, this kind of insult doesn't just cause a little passing inflammation. This is the kind of serious hit that is thought to prime the glia. So they flip that sticky switch that we talked about. And this is why repeated head impacts are taken so seriously. To add a reassuring caveat here, not every knock to your head does this. Your skull, the cushioning fluid that you've got around, the resilience of the tissue, the brain can absorb a lot and be absolutely fine. The concern is if the injury is significant enough to actually damage the neurons. Or sometimes the injury comes after you've already got primed glia. So road 2 is a breakdown of the blood-brain barrier. And this is the main subject we're talking about today. But it's also its own distinct mechanism. Here, the problem isn't an actual blow to the brain. It's that the protective gate is failing. The tight junctions loosen, and now things that were supposed to stay out in your bloodstream can get in. Inflammatory messengers, immune signaling proteins, certain chemicals, and the big one, antibodies. Once these reach brain tissue, they can switch on that glia. So a leaky barrier is, all by itself, an engine of brain inflammation. And it's thought to be capable of driving both the sticky priming and, in some cases, full autoimmune problems. And we'll look at that in a moment. And then we have road 3. So this is peripheral inflammation. This is inflammation coming from elsewhere in the body, so maybe your gut, your joints, your liver, and signaling up to the brain through various routes, including the vagus nerve, which is that big information highway between the gut and the brain, that there is a problem and that there is inflammation. And here's the crucial, almost reassuring part. Based on this model, this kind of inflammation generally is not thought to be strong enough to prime a healthy brain. So your run-of-the-mill gut inflammation on its own, we don't think is enough to flip that switch. To truly prime the glia, the thinking goes that it needs to be something a bit more serious. So a real neuron injury or a breached barrier. But, and this is where the 3 roads connect, if your glia are already primed from some earlier event, then peripheral inflammation can deliver what's sometimes called a second hit. So it can reactivate those cells that are already sitting on a hair trigger. The gut flare that a normal brain would handle quietly can light up a brain that's already been primed. So rank them now. How worried would you be? Direct neuron injury? Worrying because it primes. A leaky barrier? A wide open concern because that can also lead to priming and autoimmunity. Peripheral inflammation alone? That's the least alarming of the problems. And that usually is a problem if it's already reigniting a brain that has already been primed. And that's the framework that we're working with when we're looking at neuroinflammation and the blood-brain barrier. And everything else kind of hangs off it. So let me make a case now for why that leaky barrier, that road 2, deserves special attention. Because this is genuinely fascinating and it reframes a lot. So let's start with antibodies. Antibodies are the precision-guided weapon of your immune system. Proteins that lock onto a specific target and flag it for destruction. Usually that target is a virus or a bacteria. But sometimes, through a quirk of biology, your body produces antibodies that target your own tissue. And that's the root of autoimmune disease. Now, here's the key physical fact. Antibodies are large molecules. And so are T cells, another big immune player. They're simply too big to slip across a healthy sealed blood-brain barrier. The intact gate physically excludes them, which leads to a startling idea that's turned up in the research literature. A meaningful slice of the general population may be walking around with antibodies in their blood that are reactive against brain tissue. And for most of those people, causes no problem at all. Why no problem? Because their barrier is intact. The antibodies are circulating in the blood, but they can't get in. The gates are closed. They're locked outside the building. Now picture what happens when the gate opens. Suddenly, those brain-reactive antibodies, which were harmless their whole life, have a way in. They reach brain tissue. They bind to it. They can start causing real damage. The classic illustration people use is someone who's quietly carried these antibodies for years and then maybe goes on a heavy drinking binge, alcohol being one of the things that can stress the barrier open. And that's the event that lets the antibodies through. Or maybe there's an injury to the head or a virus that passes that blood-brain barrier. And what looked like sudden onset of neurological disease may really have been a loaded gun finally going off. And that's why this barrier is so pivotal. The danger wasn't only the antibodies, it was the antibodies plus the open door. And there's a vivid piece of animal research that drives this home. So scientists studied a brain-infecting virus and asked, why do some animals barely get sick while others have catastrophic neurological symptoms? And they used a dye that normally cannot cross the blood-brain barrier at all. And in animals whose barrier stayed sealed, the dye stayed out, the symptoms from the virus were mild. But in animals whose barrier had broken down, the brain tissue turned blue, the dye flooded in, and the degree of that dye was tracked almost exactly with how sick the animal was from the virus. Once that barrier breaches, everything can get in. That's the whole point. The severity wasn't really about the virus, it was about the integrity of the gate. So if an intact barrier, blood-brain barrier, is this important, the obvious question is, what damages it? What loosens those tight junctions? And the honest answer is that the barrier appears to be sensitive to quite a lot of things, and that the tight junctions don't have a huge reserve to protect themselves. So chronic stress on them can wear them down over time. But let's have a look at some of the main suspects. So we have environmental and lifestyle stressors. And this is where some of the more striking research sits. The barrier appears to be quite sensitive to oxidative stress. That's that cellular wear and tear from an excess of reactive molecules. Cigarette smoke is a big one, including secondhand smoke. Tobacco smoke generates free radicals, and there's research linking smoking and air pollution more broadly to barrier breakdown. Traffic exhaust as well gets mentioned for the same reason. Poor sleep is another. Studies on sleep restriction suggest that impairs the blood-brain barrier function, which dovetails with everything we know about sleep being when the brain does its housekeeping. And chronic psychological stress as well, that shows up in the research too. Then we have metabolic factors. And here's one that surprises people: blood sugar and insulin. Chronically high insulin, the kind that comes with obesity and metabolic syndrome, is associated in research with both brain inflammation and barrier problems. So fat tissue itself isn't inert, it pumps out inflammatory signals. There's enough of a connection between insulin problems and brain disease that some researchers have actually floated the provocative label of type 3 diabetes for Alzheimer's. Also in this bucket are markers like C-reactive protein, which is a general signal of inflammation in the body, and homocysteine, which is an amino acid that at high levels is associated with in some research with barrier disruption, as well as iron overload. So too much iron can actually drive a particularly nasty form of oxidative chemistry that's hard on the blood-brain barrier. Then we have the gut connection. So remember how the gut and the brain barriers are built alike? There's a regulator protein called zonulin that helps control the opening of the gut's tight junctions. And research, much of it originally in the context of celiac disease and gluten, suggests that zonulin may regulate the brain barrier's junctions too. So in someone whose system releases a lot of zonulin in response to a trigger, the gut and the blood-brain barrier could loosen together. There's also a bacterial component called LPS, a piece of the outer coat of certain gut bacteria. It belongs in your gut, not in the bloodstream. But when the gut leaks, LPS can get into circulation. Researchers call this endotoxemia, and LPS is one of the substances thought to be capable of priming the brain's glia. So the genuinely worrying stack in this model is a leaky gut plus high circulating LPS plus a leaky brain barrier, each making the other worse. So now for the hopeful part, and also the part where we've got to be the most optimistic. The blood-brain barrier appears in principle to be repairable. It can break down, but it also seems that it's able to heal. Most of what we know about the active healing of the blood-brain barrier comes from animal studies, not from human trials. And there's a good reason for that. To truly measure the animal's blood-brain barrier integrity, researchers have to examine the brain tissue directly, which is obviously not something that you're able to do in a living person. And that's why human evidence in this area is a little thinner than we would like. But let's have a look at 3 mechanisms that can help to protect this blood-brain barrier. So first, we have reducing oxidative stress. Since oxidative wear and tear is a major way that the barrier degrades, antioxidant compounds are an obvious place to look. In animal studies, things like alpha-lipoic acid, omega-3 fish oils, resveratrol, which is the compound that's associated with red wine, and curcumin, which is the compound in turmeric, have shown effects on reducing barrier permeability and calming inflammation. And the one that gets singled out most often is glutathione. This is sometimes called the body's master antioxidant, and the brain depends very heavily on this. Again, promising signals, mostly in animals, but with that human picture still being filled in, we can still see how this works in the human body. 2, we have protecting the blood vessels themselves. So remember, the barrier is partly made up of blood vessels. Those vessel walls have their own protective chemistry, including a molecule called nitric oxide, which comes in a good protective form and a bad inflammatory form. Some compounds are studied for nudging that balance towards the protective side and improving blood flow. So ginkgo biloba and a compound called vinpocetine coming up in this context. And the interesting thing about ginkgo is that it may work on both fronts. So it's actually antioxidant as well as working on that vascular front. The third mechanism then that we look at is calming those astrocytes. So those support cells, when activated, that can drive the barrier open. And that's a process called astrogliosis. Compounds that help keep astrocytes calm, they're the third angle. And interestingly, this list overlaps heavily with the antioxidants. So things like resveratrol, curcumin, and a broader family of plant compounds called flavonoids show up again and again. And then we have to look at the lifestyle side, which may honestly matter just as much as all of those compounds that we've just mentioned. So exercise. This is one of the better supported levers for brain health generally. Exercise prompts the release of growth factors that nourish and protect the brain, and the same machinery is thought to protect the barrier. The catch is that for someone with a sensitive primed brain, intensity can be a problem. So push too hard and you generate the very oxidative stress that you're trying to reduce. So it's about finding the right dose of exercise for you, not maxing out. Then we have sleep. This is a non-negotiable. We covered that sleep loss can degrade the barrier. The flip side is good sleep helps to maintain it. In a primed brain, sleep often isn't as nice to have. It's actually the thing that can determine whether anything else will work. And then we have cleaning up the environment. So if oxidative stress and pollutants are part of the problem, reducing exposure is part of the solution. So things like high quality air filtration and not living in a cloud of cigarette smoke. And then we have addressing the metabolic driver, because a high insulin can be a constant background trigger. Diets that lower it get attention here, including things like lower carbohydrate and ketogenic approaches, which can sharply drop that circulating insulin, which researchers linked to that reduced inflammation. Those ketogenic diets, they can actually help to repair the myelin damage in things like multiple sclerosis. And this is an exciting idea that's floating around. It's early research, but it is there. So these sorts of diets can be really beneficial. This doesn't mean that a ketogenic diet is quite restrictive. So it doesn't mean you should be on a ketogenic diet super long term, but it is something that we can use to bring that insulin down, to bring down the inflammation and to help to repair. Before we finish this episode, let me leave you with one more idea because it ties the whole thing together and it's a little bit mind-bending. We talked about how a leaky blood-brain barrier lets brain-reactive antibodies in. But here's a twist. The antibody doesn't even need to actually be aimed at your brain to hurt it. There's a phenomenon called molecular mimicry. So sometimes a protein in your food or a piece of a microbe happens to look at a molecular level a lot like a protein in your own tissue. Gluten is the example that we tend to look at most. Certain gluten-related antibodies appear similar or similar enough to a protein in the cerebellum, a part of the brain that they can then bind to it by mistake. So if your barrier is open, an antibody that your body made against something in your diet could actually end up attacking your brain. And we have published works mapping out a whole list of these cross reactions. But it's one more reason why the integrity of that blood-brain barrier matters so much. So here's what I would love for you to walk away with. The blood-brain barrier is one of the most important structures that you've probably never been told to think about. When it's sealed, it protects the most irreplaceable tissue you own. When it leaks, it can let inflammation and chemicals and even misguided antibodies in so that they reach the brain. Unlike the rest of you, the brain doesn't get a completely clean do-over. And the deepest lesson isn't really about any one supplement or any one test, it's about precision. The people who do well with chronic brain symptoms aren't the ones chasing a magic pill. They're the ones, and the clinicians as well, who figure out exactly what is driving it, who track it over time, who measure whether things are getting better, and who keep adjusting. The hard and valuable part here is the detective work. So if we go back to that woman at the very beginning who was told that there was nothing wrong, the point was never to promise her the brain that she had when she was 20. The point was better days, more good hours, more function, enough to keep showing up for her kids, enough to be able to do her job, enough to be there for her family. That's the real goal. And for a lot of people, that's a very achievable one. That's it for today's episode. I hope that you found this useful. If you did, please share it with someone in your life who's been told that maybe their brain fog is just stress or just a sign that they're getting a bit older, because maybe they need to hear about this episode too. Thank you for joining me on today's episode, and we'll be back next week with another episode of the Good Health Podcast. You've been listening to the Good Health Podcast. I'm Nicole Good, certified functional medicine practitioner, autoimmune and thyroid specialist, and author of Optimal You. You can find me at goodhealth.uk, that's GOODE health.uk, on Instagram at Good Health Clinic, GOODE Health Clinic, and wherever you get your podcasts. All the resources are linked in the show notes below. I'll see you next week.